is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hello and welcome to the new and improved Sky Tour Radio here on KGRAradio.com. I'm your host, the new and improved Mark D'Antonio, whatever that means, here with my new and improved co-host, Amanda Curran. How you doing, new and improved, Amanda?
Whatever that means. I'm well. How are you?
I'm doing fine. We want to welcome our wonderful KGRA listeners to the broadcast. Now, you thought I was going to say new and improved KGRA listeners, didn't you? But I didn't. No. So I'm just having fun with the language like I did last week, but I won't do it anymore, I promise. But I do want to tell you to make sure that there's a couple of announcements. Make sure you check out Amanda's Sky Tour News segments that she does on her channel, which is at DannyFan1, DHANIFAN, number 1. And it's the news of space for our broadcasting week. It's a lot of fun. She really puts a lot of effort into it, and it's a nice little companion to Sky Tour Radio. Additionally, we have a companion live stream to Sky Tour Radio, which is obviously Sky Tour Radio is here on KGRA, but Sky Tour live stream is on YouTube. And Sky Tour live stream is, on clear nights, a live deep sky astronomy view and hunt. We go looking for wonderful things in the sky. And we use these special cameras which allow us to see things in seconds, not the many minutes it might normally take. So it's really a foray into the deep sky. And it's wonderful. P&K Space Imaging does, now known as P&K Science. They do the moon and the planets. Bill New York Skywatcher does this wide-angle views to show us meteor showers and whole constellations. And Sky Tour Livestream does the deep sky. And together you can find all three of us on the wonderful website, astroimaginglive.com. if you like. And we're there. We have sometimes all three of our streams are running at the same time. It's a blast. And even when I'm streaming and I go to the other sites, I forget I'm streaming. I got to go back to my own. It's crazy. So and if you're interested in talking to us, we do have a KGRA email now. It's at SkyTourRadio, all one word, SkyTourRadio at KGRAradio.com. So tonight on Sky Tour Radio, it's going to be a little bit different. And, of course, we do have a 2-hour show now. So if you're just joining us and wondering where Commander Cobra is, well, he's already been. Okay? And we are now starting at 8 o'clock Eastern Time, 8 p.m. on Eastern Time, across the board. So we start every show with an exoplanet roundup or a slight variation. Well, tonight's going to be a slight variation. And we're going to talk about fast radio bursts that are in the news lately, and explain what they are, and also explain what this last one means and why it's extremely rare so far. Then we're going to talk about comets. It's sort of the season of the comets. There's a few comets out there now. We viewed them in Sky Tour live stream, and we've watched them, and we actually come back and take pictures of them every few minutes. And I put them together into a animated GIF file up on the Sky Tour live stream Facebook site, which is a companion site to the companion stream to the radio show. So, and you can actually see the comet moving slowly through the sky, all in a time lapse. It's really wonderful. Then we're going to have an asteroid tour de force. We're going to talk about the OSIRIS-REx program, the mission to asteroid Bennu, Bennu. And asteroid Bennu is really going to be fun to talk about. And then we also have to make you aware that next Sunday, during our live show, we're going to be having a total lunar eclipse. But the eclipse won't happen in earnest, the totality, that is when the moon is fully behind, and in the Earth's shadow, the totality won't be occurring until about 45 minutes to an hour after our show. Maybe, I think it's like that, or it's another 2 hours. I'm not sure. I'll have to look it up and make sure I get it. Either way, after next week's show, you can join us on the live stream if it's clear, even if it's partially clear. All right, we'll run a live stream, and we'll actually see the lunar eclipse live and talk about it, comment on it. But next week's show is going to be fun. We're going to talk about lunar hoaxes. We're going to talk about flat Earth. We're going to talk about all kinds of things that are nonsense. Just so if you're interested in coming on board or coming up to KGRA in the chat and just lambasting us for saying the Earth is a sphere, please feel free to do so. I'll be waiting. So let's go also and just jump right into our first topic, and it falls under the Exoplanet Roundup feature for a reason that I think is important. There are fast radio bursts coming from a very long way away. So what could that possibly have to do with exoplanets? Well, from the outside, you'd probably be right. Not really a whole lot. However, one of the possibilities is that these fast radio bursts are the communications from very distant alien races. Now, what is my personal feeling as an astronomy guy? Well, I'd have to say that I don't have any evidence of that yet, but I have an open mind to it. I have an open mind, just like I have an open mind that Tabby's star might be, it's a rare chance, but it could be that it's extraterrestrial race that is building a Dyson sphere or some type of energy collector around the star that's blocking some of the light. I mean, that's just, it is I don't leap to alien worlds and alien races all the time. I just do it because it's kind of a fun thing to talk about, and there is a chance. And see, that's all I need is a chance, just need a chance. I've looked up as a little kid when I was 9 years old. I knew I was going to be an astronomer. I just knew it. I looked up in the sky and said, wow, I feel homesick. I feel like I belong there. And so I started literally at age 9 working to become an astronomer, which is kind of rare and sort of obsessive, I guess. I didn't really have, much of a life, I guess, going on that when I was a little kid. When I was 9, I had just gotten out of the hospital from having had major surgery, and I couldn't do anything. They put me in a different school. They put me in, different restrictions, had all kinds of restrictions, because they didn't know at that time what someone who had just had heart valve surgery could do or could tolerate. Now it's very different. But the fact is, knowing that I had all this time on my hands, all I did was look up at night. I laid out on a blanket outside looking up at the stars. And even though Plainville, Connecticut, yeah, that was my town, Plainville, and it was plain. Plainville, Connecticut was sort of light polluted a little bit. I still could pick out the constellations, see meteors, capture meteors overnight. At that time, we went to the library to actually get facts. There was no Google. And I would lay a sheet out in the backyard and then come out the next morning with a magnet and go over the sheet with this magnet. And any of the little particles that stuck to the magnet were probably parts of an iron meteorite that came in the atmosphere overnight. We know now, of course, that that's partially true, and that some of those particles also could be industrial waste. But at this point, as a little kid, I just loved it. It was so much fun to do these explorations. Now, on the other hand, I did do some things that kind of sort of got me in trouble, and I bet you Amanda's thinking of this one particular incident, aren't you? The one thing I did. Do you remember what I did that was kind of crazy?
They weren't fireworks, but they were like not bottle rockets.
No.
In the sky.
Yeah, remember I made a special gas to that my plan was to capture it in these balloons and then light the balloons on fire, and it would make them.
Oh, the fire arrows. That's right.
Yeah, I actually I learned. You see, I was a little crazy chemist kid. I had a chemistry set and almost blew a hole in my bedroom ceiling when I was doing something in this little beaker, and it blew this gigantic mass of stuff up into the ceiling and stayed there and wouldn't even get over it. Couldn't even paint over it. And you believe me, I tried. I did not want my mom to find out. But I learned how to make hydrogen gas from a couple of chemicals. I'm not going to say them because I don't want to actually give it away, and like incite people to do it. But by putting some things together in a gigantic, and at the time it was a glass water cooler bottle that I had. Don't know where I stuffed these things down into that bottle, stuffed this other chemical down in the bottle, which was a common chemical, and I swirled it around and then just waited. I had to wait like 3 hours, and finally it started to work. And what came out of the top of the bottle was hydrogen gas and water vapor. So I ended up trapping out the water using milk jugs full of cotton, and kept going with the tubes through the 2 milk jugs to a final clothing bag. My father had a laundry that he owned, and I'd ride on my bicycle down to the laundry and take like 10 of his laundry bags. Of course, I'd ask him for them, and he'd give me 3, and I'd say, "Oh, okay, I need more. Because all I saw in my mind was these explosive balloons I was going to make. So I took these balloons and I cut them in half, or these bags, cut them in half because they were really tall. And, the size of a soup coat to a little kid that's tall. And I cut them in half and tape off the bottom, except for a hole for the tube to go in. And I'd fill these pillow-sized balloons with hydrogen gas. I didn't know what to expect. All I remembered was Hindenburg blew up, okay? And, as a kid, I was thinking, wow, I want to recreate that. Not the Hindenburg, but I wanted to recreate this, the hydrogen thing. So I took these, I made one balloon. It took 5 hours for the balloon to fill. Now, at the time, I didn't know that hydrogen would seep out through the molecular structure of the plastic, because it could. It was a very, very small atom. And so it was seeping out, but I was filling it faster than it was leaving. So I got this puffy balloon after 5 hours. So I it off. I took it out into the empty lot next to my house, put a piece of string on the ground with a rock on it, tied it to the bottom of the balloon, and now this thing was just hovering there, back and forth. And me thinking, okay, I have a little bow and arrow here. All right, now the arrow has a suction cup on the end, but you know what? If I just, put a little rag around that and then light it on fire, by dipping the end of the arrow in gasoline and then lighting it, and shoot it with my little toy arrow at this balloon, the balloon will break and boom, I'll get this nice explosion. So I did that. First time I missed. It went into the lot area, the empty lot, and started the grass on fire. So for the next 15 minutes, I was stomping out a grass fire that I just created. Yeehaw. So anyway, I went back and then I got closer to it and I threw the arrow at the balloon, and ducked out of the way. Nothing. Darn it all. It bounced off the balloon. It actually bounced off the balloon. So I did something else. I said, okay, darn it all. I really want to see this thing go up. So I walked right up to it with this arrow that was 12 inches long, held it out at arm's length, put it right in front of the balloon. Now I was mad. I wanted this to happen. And the last thing I remember is that I saw the little flicker of the flame at the end of the arrow, which was 12 inches, off my hand. And then I saw this huge flash. It's like a dummy, I saw this huge flash, feel this pain, and I hear this high-pitched whine in my head. I was in my head, and I'm laying down looking at the sky, and I'm going, "What happened?" All right, and in my ears, I basically remember hearing something went boom, like a loud boom. Well, it turned out that, of course, the arrow burnt through the bag, and hydrogen alone doesn't burn. You need to have oxygen with it, and of course, that catalyst was like all I needed. And so when I did that, the balloon exploded, and I got hit in the chest by this little shockwave, knocked me right down on my butt. Okay, I was right there next to the balloon. I mean, was I thinking? No. So I'm lying there with a headache, hearing this high-pitched, in my head, and I get up and say, instead of saying, "I'll never do that again," I said, "I got to hurry up and do that again." So I went right out in the backyard where I had this little still making hydrogen gas, attached another bag, and then went into the house and kept checking it all night long. Anyway, So that's kind of the stuff that I was into as a kid. I was always trying to figure stuff out. And some of it was innocent. Some of it was not. Okay, maybe one day I'll talk about my Estes model rocket forays. That's fun. Okay, and that's another one. But and that's sort of a little side. Hopefully there's not too many of you shaking your heads out there. I know Amanda's probably shaking her head right where she is.
Well, I love that story, and it's so weird because fire arrows are not the first thing that jumps to your mind, but I remember you were shooting something up and it was exploding. It was something you made yourself, and I knew it wasn't fireworks, but yeah. So, Legend of Zelda. Who else has fire arrows? Link and Mark.
That's funny. I wonder how many people remember Legend of Zelda.
The cool ones will.
Ooh, hey, that's interesting. You just called a good portion of our audience not cool.
Our audience is the coolest, and they all know who I'm talking about. They're laughing.
Well, they're all
visualizing it, and you do have a green hoodie too.
That's true. I do. I do.
Oh, come on, guys! Give me some memes.
Not on purpose, I swear.
Use your Photoshop. I want to see pictures of Mark as Link.
Oh man.
Their fire arrows, this little boy.
It was fun. It was fun. But see, this is the life of an astronomer, guys. This is what we do, Now,
fire arrows aren't astronomy.
They aren't. They're not. But
the chemistry. I'll give you the chemistry part.
That's right. The chemistry. The chemistry to get to the point where I used these fire arrows, which of course, remember, didn't work. I had to hold it there and touch the balloon. It's like, just stand here with this. Just hold that match near the wick of the dynamite, okay? Yeah, I know the wick's only an 1/8 inch long, but don't worry. What could possibly go wrong? I wasn't thinking. So the next one I actually made like 5 or 6 generations of these hydrogen balloons, and a few got away. They got loose, and but the next generation I used longer sticks. And I remember watching the stick just go sliding through my hands at high speed in the other direction. I saw the flaming part of the stick go right through my hands and kept right on going like a spear, because obviously the shockwave from the balloon just like blew right through my hands. Hey, where'd it go? And, but even you could feel a shockwave hit you right in the chest, and that vibration, that shock, that was, I don't know, that was the most cool thing. I just loved it, I could have worked for the Bureau of Mines, as a demolitions engineer or something. I don't know. But it's okay. These days, I don't play with anything more explosive, than, I shouldn't even say. But anyway, I don't play with anything explosive these days anyway. I really don't. But I do think that when you're learning science, that will take you down some really strange paths. And that was a strange path, yes. A little bit risky for a kid, too, by the way. Not as risky as setting the whole backyard on fire, which is another story. But
not as risky as almost setting the house on fire.
Oh, yeah, no, that's true. But, but you know what? I wasn't setting the house on fire. I wasn't even coming close. You got to remember that I was a precocious, science-oriented kid, so I had to go and explore. I had to explore. I never did anything malicious to anybody. I just didn't. I wasn't really that way. I was like one of these kids that just had to explore and kind of be on my own, do my little thing. Ask the adults that knew the stuff about the stuff that I wanted to know about, and they would tell me what they knew. And go to the library and look up books. And they always tried to tell me, the children's section is downstairs in the basement, which it was. I didn't want the children's section. They didn't tell you how to do some of these things. I wanted the adult section. And I had a librarian say, are you trying to find a book for someone? I said, yeah, for me. Oh, well, the children's section is downstairs. No, I know. Oh, well, okay then. What are you looking for? And I said, I want a chemistry book. I need to understand a couple of chemical reactions, I said. And this lady looked at me like I had 2 heads. It's like, really? I go, yeah. Well, that was the beginning. And, of course, I had all these books. I had a huge library. I had literally, how people have, a few books they like, and they're kind of on their nightstand or they're up on a little shelf. I had a shelf that was around 12 feet long, had around 9 layers of shelves from floor to ceiling, stuffed to the gills with books. And I had filled them so much that some of the books were on top of other books on their sides, you know. So, I mean, I had really a lot of books. And I've retained only a small fraction of those over the years because of nostalgia reasons and sentimental value. But let me tell you, this was a lot of fun. You know, reading, like the most favorite, reading and learning stuff. I don't know why, but learning was amazing. And I think that that's sort of missing in our schools today and with contemporary children. Reading is something they get on the internet, or it's something they get by doing a search in Google. Reading is not something they do by picking up a leather-bound collection of paper pages and reading and looking in there. You know, so there's something to be said for that. You know, now, granted, for the stuff that we do on Sky Tour Radio, we're getting a lot of information from the internet as well as out of my defective brain. But the thing that's really interesting is that I think that all of you are benefiting from the fact that I did spend so many years just looking at those printed letters on pages of paper. And someday books will be sort of a collector's item because we're kind of migrating away from books and going to electronic distribution of things. But having a real book, that's a real cool thing. You know, Amanda, you remember this. We did readings from a book called The Architecture of the Heavens and a Series of Letters to a Lady. And this is I bet you were, because I have that book right near me, right here. It's a physical book from the 1800s about astronomy. And you know, folks, back in the 1800s, there were astronomers, but we didn't know a whole lot about the sky back then. So the only way to really discuss it in a way that could be taken half seriously was to almost make it a glamorous presentation. So how do you glamorize something you know nothing about other than a fuzzy photo that you may have taken or what you observe with your eyes? Well, the way you do it is you make it poetic, you make it flowery, and you make it in a series of letters to the one you love. I mean, that's what this book was about. So when you read the book, when you read some of these passages, and we've done this on past show, I
think it was our Valentine's Day show, actually.
I think you're right. I think it was. You're right. And on that show, good memory. On that show, when we read this series of passages in the book, the one thing that we found was that there's no female in the world that was going to understand this unless they had a PhD in astronomy like the guy writing it. He was saying it in flowery language, but he was making PhD commentary, you know, and the average person on the street would never have a chance of understanding this. So you say to yourself, not without, an advanced degree. That's the point in astronomy. And it has to be astronomy. If you had an advanced degree in chemistry, well, no luck. If you had an advanced degree in metallurgy, well, no love there. Okay, so you have to have a PhD in astronomy to understand some of the things that he was getting at. Now, that was a PhD equivalent at the time in the 1800s. That's where I'm going with that. The book was written for different reasons. There was almost political reasons for writing the book this way, because they had to be able to get their points across and state their beliefs, but not lose the audience and not make it sound like they're making stuff up, because that's pretty, that's pretty close to being one of the only alternatives you have when you don't have a whole lot of science to back up everything you write. That all said, I think that the best thing is that our wonderful world now has this beautiful research that we can do and that we can back up everything. And I know I mentioned these fast radio bursts, and we'll come back to that, in a little bit after the break. But I do want to just start by saying the fast radio bursts are things that are kind of like writing about astronomy in the 1800s. Why? Well, because fast radio bursts come from the other side of the universe, literally the other side of the universe. They're bursts of electromagnetic radiation that last only a few milliseconds, a few thousandths of a second, and we don't know what causes them. We just sort of know where they come from. We don't know what causes them. However, the amount of energy released by these, literally in a microsecond, these millisecond bursts, is the equivalent of a decade's worth of solar energy power output. Can you believe that? The sun is a massive star. Its output daily is massive. Imagine 10 years worth of that output all summed together in just a few thousandths of a second. That's what a fast radio burst is, and we don't know what causes it. I think that is incredible. And that's, of course, where we start in tonight with the remaining hour and a half of our show. So I think that when we talk about these, we want to put it into a perspective of, when the first one was seen. And the first one was seen back in, literally 2001. However, it was archived because no one knew what that was. It was just data that was captured and archived. When somebody was going through the data in later years, in 2007, they actually found it for the first time. And they do seem random, and they do come from very, very far. Now, how do we know that they come from far outside our galaxy? Why can't they just come from a few stars away? That's a very good question. How do we know this? Well, when a full electromagnetic pulse leaves a galaxy, and it's journeying through space. First, it's interstellar space in its own galaxy, perhaps. Then, it's intergalactic space, the space between the galaxies. As it's coming here, it's encountering dust and other gas that's actually in between galaxies. And that slows down, if you will, certain wavelengths of that light that's in that pulse. Now, the light is in the radio spectrum, so it's longer wavelength stuff, okay? But certain wavelengths are more toward the blue end of the spectrum, that is to say, less red, okay? And some are more red, okay? Well, this travel through space over a long distance will cause that pulse to sort of lengthen, so to speak. And that will mean that the pulse, when it finally gets here, is going to take some time to be detected from the beginning of the pulse to the end of the pulse. Okay, now that timing and that length of the pulse is called the dispersion. Okay, dispersion. And dispersion can tell us, if we know how much there is, dispersion can tell us how much material that burst actually traveled through before arriving here. And the way it works is like this. You time the pulse's arrival from the shortest wavelength to the longest, high energy to low energy within the pulse. And that tells us how much material was encountered from there to here. Now, here's what's important. Since these originate in very distant galaxies, fast radio bursts, help us determine the density of matter in between the galaxies. In other words, whatever's between the galaxies and whatever mass and whatever density it's at, the dispersion or spread of the wavelengths from this fast radio burst will tell us how much of that whatever is there.
And it's in between the show.
Yes.
Breaks. And unfortunately, we're coming up to our first one. So more on that in a minute.
All righty.
Thank you.
Hello and welcome back to SkyTour Radio. I'm your somewhat beleaguered host, Mark D'Antonio, and I think that on our last break, I just wanted to talk so much about fast radio bursts that Amanda had to come in and kind of remind me that we have to let the station make some money. We had to go to some breaks.
Sorry, I hate doing it, and I hate interrupting for something like a break too, but
You know what
What are you going to do?
She had to do it, and I'm certainly grateful that she did. And hopefully you are too if you pay attention to the sponsors. So when we were talking about these fast radio bursts, we said how there are these electromagnetic pulses that come from this far-off galaxy, and I said this, well, the way we know is by the way they get stretched out, basically, by traveling through other gas, other dust, in between galaxies on the way here. So this dispersion, this spread that we see, is really something that tells us how far away they are, and we can see where they came from. Now, you might say, well, how many of these are occurring and then these just start? Well, the answer is no, and we're going to see why shortly. But I want to talk about in the news lately because a new fast radio burst was discovered, and like there's only one time before this has happened, but like this one previous one we saw, we've seen over 60 of them so far, but like this one we saw in the past, this one's a repeater. It repeats, bum, 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 all in millisecond pulses. So, but then after, by the way, after then it repeats for a while, it shuts off, never to be heard from again. That's what's so perplexing. Okay, so the first repeater was given the extremely attractive name of FRB 121102. I know you're all saying, "Wow, that's amazing! That's a wonderful name." Yeah, no, it's not. But look, astronomers, sometimes we don't have a whole lot of imagination. I can imagine that's probably the truth. But it was discovered in 2017, and it produced no less than 93 separate little millisecond pulses before it turned off forever. And it's like, interesting. So it's a one-time event in general, or just a one-time event with some repeats. So that was the first one in 2017. And then this last one that we heard from, okay, is one that also makes it unique because it was also a repeater. And that new repeating fast radio burst was recorded by an instrument in Canada called CHIME, and it stands for Canadian Hydrogen Intensity Mapping Experiment, which I knew you all knew. Don't worry, I had to look up what the I meant. I didn't know what it meant, but it was hydrogen intensity, and I knew mapping experiment. But anyway, what was it? Well, it's basically just an array laying on the ground. You don't aim it, you just lay it on the ground, and as the Earth rotates, it listens. It looks up in the sky and it senses. Now, it was listening for any kind of fast radio burst, and the fact is, when you just get one, and it comes through and it's gone in a millisecond, well, that doesn't really give you enough information to help you figure out what it is. So a repeating burst, on the other hand, especially from the same event like this, well, that means we can probably identify the source. But what about that source? What do they think these are? All right. Now, we really don't know what they are, but here's what the possibilities are. Now, first of all, the signals are the most powerful signals we've ever seen. They're emanated from extremely distant sources. Okay, this latest one that I was just mentioning from the CHIME instrument, it repeated 13 separate pulses before it shut off. And here's what's interesting. They were emanated from this last one. They were emanated from a galaxy 1.5 billion light years away. Okay, now, you think about this. When that pulse was emanated and originated in that galaxy 1.5 billion light years away, what was going on here? At that time, we were just cyanobacteria. We were blue-green algae. That's the only life form that was on the planet at the time. Amazing. The beginnings of our oxygen atmosphere began with we didn't even have an oxygen atmosphere really at that time. All right, and our oxygen atmosphere was helped along by these little bacteria. So I'm sure that there's fast radio bursts, we call them FRBs, that were emanated long before life actually existed at all. And this, this is true. And if they're as common as it appears, it's estimated that we kind of miss probably thousands of these a day. Thousands of fast radio bursts a day. Now, these events are going to rewrite our physics and astro books, guys. I can tell you right now. Here's why. Simple supernovae, again, some of the most powerful explosions and cataclysmic, destructive events in the universe can't cause them. Can they be caused by merging neutron stars? Well, maybe. We know they create gravitational waves. We've seen those with the Laser Interferometric Gravitational Wave Observatory. That's LIGO, L-I-G-O, right? We talked about LIGO at one point. Merging neutron stars create gravitational waves, but they can't, maybe they can create this, but we don't know a mechanism by which they could. Simple and complex supernovae can't cause these. What's going on here? Hypernovae, even bigger than supernovae by far. That's not the energy level we're talking about. There's something else. Something else is going on. Are they the result of a cataclysmic collision of black holes? Maybe. But, I'm just saying words. We don't know what that entails yet, to make this kind of power output. Then, here's the other option. Are they artificial signals sent from an alien race as a beacon to other life in the universe? Are they transportation beams of some sort, far beyond our understanding? Transporting data, information, beings, on some trip, far out trip. And then just a word about these vast distances these things have traveled. As I said, astrophysics currently thinks, the astrophysicists think that as many as 5,000 per day are missed. Now, the Earth is 4.6 billion years old. The universe existed for over 9 billion years before the sun ever formed. Some of the fast radio bursts, may be found that emanated from their source before the sun was even born. Can you imagine that? So we have, we have a definite strangeness going on in the universe, And for whatever reason, these things started on their way long ago from whatever amazing origin they probably all share separately. So the overall picture then is that these FRBs, all right, these fast radio bursts, come from way past our galactic neighborhood. Now, what is our galactic neighborhood? Well, it's the Milky Way. It's the Large Magellanic Cloud and the Small Magellanic Cloud. I'll tell you about those in a second. It's the Andromeda Galaxy, which most of you know. It's the galaxy in Triangulum, right near the Andromeda Galaxy, relatively, plus 25 additional, quote-unquote, local galaxies. Now, the large small are clouds of stars that were seen by Magellan, obviously, and they are in the southern hemisphere. We don't get to see them up here. What they are is something called dwarf galaxies. And these dwarf galaxies are sort of, they have always been thought to be associated with our own galaxy, just like the Andromeda Galaxy has two little galaxies associated with it. But just a little note on that. Classically, those two dwarf galaxies have been considered our own, attached to us, orbiting us. Part of our gravitational interaction would be with them. Well, it turns out that might not be true. It might be that they were just passing us. Now, how can I say that and why? Well, a study was done of our local neighborhood of galaxies, and that's an odd term, local neighborhood, considering the vast distances with galaxies, right? And it's shown that these two satellite galaxies to our own, the LMC and SMC as we call them, Large and Small Magellanic Clouds, may not be gravitationally bound to us, but on independent trajectories going their own way. Now, what does that mean to us? You might say, well, big deal. Actually, here's what it means. It means, if true, then the estimate for our own distance from the galactic center could be wrong by up to 12%. Now, currently, the estimates put us at 28,000 light years from the center of our galaxy, with an uncertainty of 1,650 light years either way. Okay, plus or minus, right? Well, that means that our center from the galaxy could be wrong by as much as twice that uncertainty, or 3,400 light years or so. So we could be closer. And I think that's pretty cool. Now, what does that mean? That means a whole lot of things change. It means that our estimate for how many times we go around the galaxy since we were formed has changed. It'll mean that we think we've gone around the galaxy about 19 and a half to 20 times since we've formed, but that's from being 12% further out. Maybe it's less, or maybe it's a little bit more. We're not sure. If we're farther out, then it'll lower. If we're farther in, well, then it'll get higher. So maybe we actually have gone around the galaxy core 22 times, 24 times. Who knows? So it just depends. If this is correct, then we're going to be changing a lot of the physics, which is kind of interesting. Now, bringing the discussion closer to home and to put it into perspective. And before I do this, I really do want to pause for a moment and give anyone in chat or give Amanda a chance to ask a question if there's any questions out there, because I'm sure that, fast radio bursts are one of these topics that can generate a lot of questions. So I'm going to stay quiet until I hear from Amanda.
Okay, well, I'll see if anyone in chat has any questions. Give them a minute to catch up. I have a question, but I'm scared to ask it because it's obviously not what I was thinking. You said the first fast radio burst was discovered in 2017. Is that what you said? That can't be right.
The first one was archived and not found back in 2001, but then it was found in 2007.
Okay.
But then the one we're talking about, okay, was one that was discovered in 2017, and it turned out it was 13 pulses, which is kind of cool.
Okay, but you said the first one recorded. The first one recorded was 2001.
Yes, but it was recorded and not noticed because we didn't know we weren't looking for it. We didn't know what to look for. So clearly, it wasn't flagged as something because it was only a millisecond. It was only a very, very small amount of time. See, so they didn't notice it.
Okay, so I see. I was thinking something, and obviously it's going to be something totally different. If this is too big of a topic to take on tonight, just let me know. We'll bring it up on another show. What's the wow signal? I thought that was a fast radio burst, and that was way before 2001.
Yeah, the wow signal was another signal that was detected coming from space.
But not a fast radio burst.
It wasn't an FRB, no. But
okay.
It was a signal that to this day is still not explainable. It hasn't been explained as, a Russian satellite passed over the antenna at that time and it recorded the actual Russian satellite. Okay, we have had those kinds of close calls, false identifications. That has happened. We do have a presence in space, folks, and sometimes it's not all that pretty. We do make a lot of noise here on this planet. So, but no, that's the wow signal is not and was not a fast radio burst. I think that's kind of a really, really interesting topic. So, all the fast radio bursts take place and of course they're called FRBs, as in radio, because they all occur within that radio band. All right, so they're all in that same location, and that's the Blue Orbs question about whether.
I was just about to say we do have a few questions coming in. You got that, okay?
I love it. That's all. That's very good.
That's our good friend Charles.
Yeah,
how broad is the band of FRBs?
Yeah. Yeah, and it's the radio band. Now, the other thing is it do these FRBs contain data? And that goes back to, are these extraterrestrial intelligence in nature? And the answer is that there's been no. I don't even know if there's been an attempt to look at these as intelligence signals. I know there has been the thought that they're intelligent, but I do find that when you say, can you decode these? Is there a way to decode them? I don't know. I don't know about that. The F are really of a similar frequency to each other, but they're random. They're all over the place. They're coming from all over the universe, from very far away. Now, this, to me, does not lend itself to an extraterrestrial intelligence source. Why? Because it would mean that this extraterrestrial intelligence, all these, say, separate intelligences throughout the universe have all happened upon the same exact communications method. I don't find that probable or plausible. I do think that perhaps there is a intelligence out there that has managed to figure out a way to travel the entire universe by maybe going, this is a whole nother show, using a different propulsion method to get it themselves to different locations in the universe. And you might think that sounds like science fiction, and right now it is for us. A warp drive, for instance, an Alcubierre drive that we've talked about a few times on SkyTour Radio and SkyTour Livestream. An Alcubierre drive is something it would actually take probably a lot longer, well, certainly a lot longer, as fast as it is, as mind-blowing as it is, to be able to go to Alpha Centauri in 5 days versus 12,000 years. It's still way too slow to travel, say, to the center of the universe or center of the galaxy. Never mind the center of the universe, actually. So it's really a very different, type of possibility here.
I have a question.
Yeah, go ahead.
What all, I don't know how to phrase it, what all have they done with these FRBs? Like, have they slowed them down? Have they reversed them? Have they tried to match it with, like, Morse code? Like, what all have they done with it? Like, testing, experimenting. I don't know how you would phrase it.
No, that last sentence is the best one you said. Okay, testing and experimenting with the FRBs to see what they may or may not be. That's exactly what's going on. It's going on with every one of the FRB teams that are checking these things out and seeing them occur. They're trying to see what they're from. A lot of the astronomy community is thinking that FRBs are naturally occurring for some reason that we don't understand yet. Now, in all fairness, not everything that we understand is an extraterrestrial intelligence doing something. All right? Personally, I have an open mind to that. I'm not saying it is. I'm not saying it's not. A lot of astronomers may just say, no, that's not extraterrestrial intelligence. What's wrong with you? Just because we've never even been able to show that an extraterrestrial intelligence exists yet. But once we do, then those astronomers will kind of lose some credibility or whatever it is. I don't know. I don't care. I just think that we want to keep our mind open to all the possibilities, not just some of the possibilities. Well,
it's just we did something like that. Like, we sent a record out into space, and
yes, that's right.
Different pictures and different codes, and
right,
just for any kind of way they could decipher something. So why wouldn't that be? I don't know. Why wouldn't they just play around with it and just see if it matched anything we have here?
They may have been doing that. I don't know. It wouldn't match something that we have here. It would probably match something that seems different from what we understand as FRBs are. However, it would also probably show some type of intelligent construction to the message. And based on what we think is intelligent. How about that? Yeah. Again, we've talked about this before. The universe, I think, is primarily a carbon-based universe. Why? Well, because carbon-based building blocks of life are made here by the Earth automatically by the Earth's atmosphere. It happened the whole time that the Earth was forming. They were delivered by meteors and asteroids and comets. Water is important to life on Earth, so it's probably important to life elsewhere in some way. Not all life, but somewhere. So that's the interesting thing. And I know that, when we look for other life forms, most likely, and I think this is probably true, we're probably going to have some type of common ancestry, even if we have to go back to the very earliest DNA structures. I think that DNA, being like it's prevalent here on Earth, is probably going to be a prevalence elsewhere too. And we'll probably find it if we find microbes on Europa or in the deep soils of Mars. I suspect we're going to find that there is similarities to the microbes we have here. Why? Because I think that it's based on the universal starting point. And I think that these are templates that the universe creates, So I think that that's interesting to us, That makes a lot of sense. And I think that's where science is going to go, is trying to compare life here to life there when we find it. And I can just see tons and tons of papers and conferences on the extraterrestrial life found in Europa's oceans, in the European oceans, versus the life forms found in our oceans. We're going to do these equates and say, oh, this one's like this, that one's like this is not like this because of this. The evolution is different, absolutely very different. We suffered extinction level events. We have a much larger planet. We have higher gravity. Our oceans are deep, but certainly not as deep as the European Ocean could be. It could be 90 miles deep or more, 60 miles deep. We don't have a 60-mile deep ocean. We have a 7-mile deep ocean at the greatest almost. So it's not. It's very different, but because Europa is lesser gravity, then it's going to give rise, if there's creatures there, it's going to give rise to different types of life that inhabit those different depths. Now we call below the surface and above the bottom, sort of in the middle there, we call that the midwater realm. And midwater is the places, for instance, where certain fishes occupy that never come to the surface or never go to the bottom. And they live in the midwater region. Well, maybe there's going to be midwater life that inhabits anything from 4 meters down to 40 meters down on Europa. And they'll be very, very different from each other. So it's just incredible, Now, I think that, when we talk about these different types of life forms and the possibilities, we have to keep in mind that we're only looking at our own solar system right now and looking out from it to check out what's out there. We haven't visited Europa yet. Well, not really. The Europa Clipper may be able to visit Europa and find something we don't know. We visited Titan. We landed on Titan. Ta-da! We're fantastic. But you know what? We're also finding things on Titan that we didn't realize could be there. It's just amazing. The new data that's coming out, and I tell you, we're going to get a lot more information as this continues, as we get this continuance. So I'm pretty pleased. I'm pretty pleased with where science is going now. And I just want to leave you with this before we go to break here. Okay, right now, we've only just begun to explore our own solar system. All right. And we're basically having, let's say it's a revolution. It's a revolution in science. We're seeing all kinds of things. We've actually visited a comet several times now. We visited a comet many years ago. We visited a comet by doing these flybys of a comet, and then we actually landed on a comet. All right, and it was comet 67P Churyumov-Gerasimenko. All right, the Rosetta mission, and that provided us with an amazing view of what a comet looks like. Now, we're going to talk more about comets after the break, because that's sort of a close-to-home science that we kind of have something that we can talk about now. But we'll talk about that soon, and I look forward to coming back to you right here on KGRA Radio. This is Mark D'Antonio on SkyTutor Radio with Amanda Curran. Welcome back to SkyTour Radio. I am Mark D'Antonio, your host for tonight and all nights on this radio program on KGRAradio.com. I want to continually mention that my audience from KGRA is probably the best audience. And I know you think so too, Amanda, don't you? Yes, she does.
I do.
She has a mute button sometimes, and I think that she probably had the mute on. That's okay.
Well, you don't want to hear me typing, and I'm getting great questions from chat. So
fair, our chats are very active on our programs. I absolutely love it.
Yes,
and you guys keep them coming. And like I said, don't forget SkyTour Radio at KGRAradio.com. is our email address. And we check that email, and we will take your questions there as well. Now, I mentioned before the break that we're going to be talking about comets a little more in detail, and we're going to, because the comets that we see in the sky, especially in Sky Tour Livestream, we have seen these comets. They look like these beautiful greenish objects moving through the sky, sometimes a little bluish green. But the thing is, we know that comets are these little interlopers that actually will come and go. And some of them are periodic, and that's what that P, by the way, is next to the number. Like, there was one in Sky Tour Livestream we saw called 46P, meaning periodic, and it was Wirtanen, 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 okay? 46P Wirtanen, and that was a comet that came and went. We watched it, we took lots of pictures of it, and we created this animation which showed it moving over like an hour of time. And you can clearly see it moving against the stars. So you're looking up at the sky, you think, wow, the universe is static. Nothing moves. Yet there is something moving. We can do the same thing with some asteroids. And we can even do the same thing with some stars. Barnard stars, for an example. It moves across the sky, not daily, not monthly, but over a period of 4 months, you can detect a difference in the movement of a Barnard star. It's never in the same place twice, because it's always moving. It's so close. It's 6 light years away. It's a little further away than Alpha Centauri, but it has a high motion relative to the sun. So we actually see it whipping through the stellar neighborhood, if you will, another neighborhood term, which makes no sense, considering that we're talking about, the distance to the stars, But, that said, comets we can see moving, and we have many times in Sky Tour Livestream. So please join us at Sky Tour Livestream. It's free. It's on YouTube. It's Sky Tour Livestream with Mark D'Antonio. You can come in here and hear, and Amanda's the co-host there as well. And we work together to show you the wonderful deep sky. So hopefully you'll join us there. Now, when we talk about comets, and we want to talk about how we see them moving across the sky and their colors, we're going to address their colors soon. But first, we're going to go off to a seemingly unlikely place. We're going to go to Europa at Jupiter and Enceladus at Saturn. Now, why? Well, Europa is a 1,950-mile diameter moon of Jupiter. And Enceladus is just a 340-mile diameter moon at Saturn. Now, interesting thing. We have found some very odd things happening at Europa and Enceladus. And I think it's kind of interesting that in the movie, the science fiction movie, they speak to 2001: A Space Odyssey, 2010. The year we made contact, is that what it was? 2010. Well, anyway, that movie 2010 ends with a dire warning to us, and I think it went something like this. And I am shooting from the hip on this. All these worlds are yours except Europa. Make no landing there. Use the others together. Use them in peace. Something like that. And I thought that was kind of funny, considering that way back then we didn't really understand whether Europa might have life on it. There's also a movie out called The Europa Report, I believe, and it's a fascinating movie about a manned, human occupied trip to Europa, and that's one to watch if you haven't seen it. But anyway, so Europa is captivating the attention even as far back as when 2010 was made, before we had any of the really good data to actually suggest that there might actually be a habitability capability. I like that, habitability capability at Europa. And what's by habitable? What do I mean? Well, I mean that it has that ocean below that ice mantle that's over its whole surface. Clearly, it has no real atmosphere. There is water ice that's actually surrounding Europa, and then it falls back down to the surface and remelts and then goes back inside and gets spewed out again because there's geysers at Europa. All right, and these geysers are spewing water, as we can tell. But Enceladus at Saturn is only 300 miles across, but its southern pole might have a southern pole ocean under its surface. We think it does, because when Cassini, the Saturn probe that's now met its demise by plunging into Saturn, that was on purpose. The Cassini probe was able to show that there are hot spots that run like ridges underneath the surface of Enceladus at the South Pole. Now, why is that important? Well, we see these geysers on Europa that are spewing H2O, and we see the Enceladus geysers that are spewing diatomic hydrogen, H2. Okay, so two hydrogen atoms connected. And that's interesting because we see this very same thing happening at hydrothermal vents here on our ocean floor on Earth. It's different, but it's the same in a sense. Hydrogen combines with carbon to form CH4. That's methane. And we know that at our hydrothermal vents, methane is a food supply for microbes. Microbes are a food supply for these other filter feeders. And filter feeders are a food supply. It goes on and on and on, as you can see. It goes up the chain. So could there be microbes at Enceladus, at this South Pole area on Enceladus? Well, we don't know. We don't know. We know pitifully little about our solar system's life forms, if we can say it that way. There's also thoughts, and some of you out in the chat are probably thinking about this, and some of you listening are thinking of this. It's possible then that we might actually be able to find some form of life on Titan. And we know that science shows us that Titan is basically a deep freeze. We don't know that there's any life forms that can survive a deep freeze like this. Water's as hard as granite on Titan. It's just not possible. So what could possibly live there? Well, we don't know. But we do know that in Antarctica, there is life in the most inhospitable places we've ever found. There's life in the Patagonian Desert in South America that is just shouldn't be there, but it is. Okay, there are no lifeless locations on Earth. The hottest mineral springs have bacteria that love the heat and love that material, and the coldest areas on Earth have creatures there that can't survive in anything warmer. So we're talking about a variety of life forms here on this planet, which kind of go across the gamut. So Europa is going to be cold. No matter how you slice it, Europa is cold. But deeper in its oceans, all right, say, 25 miles down, which is something that we can't even fathom. Get the joke? Can't fathom. When we go down that far in an ocean, you might think, wow, the pressure must be crushing. Here on Earth, it would be crushing. But on Europa, only just under 2,000 miles across, the gravity down there is not going to be that strong. The weight of the water overhead is what's causing you to feel that pressure. Well, the weight of that water on Europa is going to be far less. So we could actually take a regular submarine. If we made a sub, they could go there. We could take a sub probably all the way down to the bottom of the European Ocean and be okay with it, because of the fact that we have a lower gravity at Europa. So the weight of the water over our heads is going to be a lot less. So Enceladus might have life in the microbe world underneath its southern pole cap. Europa might have life in its deep ocean and possibly in the midwater regions, lower, deeper into the European Ocean. And we know that light is not necessary. We know that photosynthesis, that is, plants converting sunlight to energy, is not necessary. We know that plankton don't have to exist in Europa for life to exist. Why? Look at our own oceans. There's areas in our oceans where life is absolutely abundant. In fact, it uses bioluminescence. They create their own light. That bioluminescent creatures live only in the realms where there is no light. And some of them have evolved away their eyes. So there's creatures in caves that have never seen the light of day for hundreds of thousands, millions of years. And they have lost their eyes. They've evolved away. They've just not needed them anymore, so they were selected to be removed. And they're a source of infection if they get poked. They're, something that could get in the way of the continuance of the organism. One organism at one point mutated to be eyeless, and wham, that just set in motion a chain of events that selected the sightless creature as the successor to the sighted creature before. That's evolution, okay? So the question I ask you now is, if we talk about then there's possibility of life at Enceladus and Europa, what does that indicate for us? Does it have any meaning for us? And then, this goes back to, don't forget, we've been talking about comets, right? So how does this all relate? Well, I'm going to get there. We're almost there, actually. So if it has meaning to us, it has to have some meaning that is in terms that we can understand. So life on Europa would take the form of some type of organic compound, such as those seen in our deep oceans at the hydrothermal vents. So, as I said, they spew methane. They form this little oasis. This methane-eating bacteria comes through and, loves to, eat the methane, and then creatures eat the bacteria. It's on and on and on. Now here, okay, the reason that happens is because we have tectonic plates. Now, again, our crust, you think of it as cooled lava, okay? And this cooled lava is something we're living on, guys. And those plates have big cracks along their edges all the way around, many tens of thousands of miles long overall. And those cracks, where they meet up against each other, one plate ends up getting pushed under the other plate, all right, and the other one rides up on it. Okay, that's happening at where the Pacific Ocean plate and the North American plate meet. Okay, the North American plate is doing that same thing, and at the Mid-Atlantic Ridge, that's the crack of the North American plate, and that's spreading outward. So from the center of the Atlantic Ocean, it's spreading to the west, and then spreading to the east on the other side of that Mid-Atlantic Ridge, and that's sort of like it's regenerating material from the interior. Okay, so what happens as these plates are moving across the surface of the Earth? There's areas in the crust at the bottom of the ocean that are kind of thin, and the heated areas from the mantle below the crust can poke up through in different locations. And in those hot spots, they're called, sometimes we'll see volcanoes. All right? And the thing is, when you look at how tectonic plates work, they move, So when you look at, let's pick one. Let's pick the Hawaiian Islands, okay? The Hawaiian Islands are a chain of islands. They go from the northwest down to the southeast. Those islands were born one after the other when the islands, which are traveling on the crustal plate of the Pacific plate, passed over the hot spot in the mantle below the crust. And in that hot spot, the volcanic action was such that the magma could reach the surface and become this lava, and an island was formed. And that's how chains of islands are born. They're born in fire. Hawaii is famously beautiful, but it was born. The Pacific plate's moving to, and the hot spot right now is underneath the Big Island of Hawaii, and that's the youngest island in the Hawaiian chain, right? The Big Island itself. And they're older, moving up to the northwest. They were over the hot spot earlier when the Pacific plate was there, and that's drifting, all right? So you can see that we're getting this action with the crustal plates moving like that. So the next oldest is Maui, then we have Kahu'ulawe, and then Lanai and Molokai, and then Oahu, and then further northwest is as Kauai and Niihau, and that's those are the oldest islands, So I think it's pretty interesting. And incidentally, if you want to learn how to speak Hawaiian, for words that have like two vowels in them, like Kahoolawe, you pronounce the two vowels. You pronounce all your vowels. So it's kahu'u, lawe. So kahu'ulawe. All right? Things like that. So nihao would not be nihao, Niihau. It's niihau, that kind of thing. So you always pronounce each vowel. Just little thing that I discovered. So the question is here, life on Earth is found everywhere, okay? And in the most acrid pools and the most cold wastelands, all right? So it seems like a lesson that the universe has been teaching us, doesn't it? Life is tenacious. The historical record is full of survivors, okay? And I mean survivors rather than, the opposite, because if we go back to the Permian era, 250 plus million years ago, 96% of all marine life was extincted, as I'd like to say, during the Permian dying, it was called, the Great Dying, and 70% of terrestrial life was extinguished. Now, that's what happened. Now, all of that extinction led to change, and these life forms just changed and came back differently. So the lesson the universe is teaching us is that life changes to meet the challenges posed by environmental stressors. It's a long-term process, okay? Life changes to meet the challenges posed by environmental stressors. And we call it evolution, okay? And how is evolution actually enacted? It's enacted by mutation followed by adaptation, okay? The best suited adaptation is selected for continuance by its success in the new environment, see? So, and just a little side note, we hear about evolutionary dead ends in the way life is developed. Dead end is a quote unquote type thing. Okay, what does that really mean? Did Homo habilis wake up one morning and say, "Oh man, there ain't no one left"? Of course not. All right, but it's about transitions that take many generations in the short term and tens, hundreds, thousands, or millions of years in the longer term, and it's about blending. One species becomes, blended with the next. Did Neanderthal thus die out and be done? No. It blended. It was usurped. It was absorbed into another line. Okay, how do I know this? Well, I'll give you an idea. My nephew did his genetic profile done. And you know what? He's 2% Neanderthal. I swear to you, it says so. 2% Neanderthal. I think that was hilarious. And I told him, never admit that in public. And I'll never give his name because he'll never hear the end of it from his friends. I can tell you that. So clearly, this absorption happens. And so life changes, okay? So could organic compounds from some other location in the solar system have been transported here to change, mutate, and adapt, okay, and be selected for success? Did this happen? Do we know whether this happened or not? That's called panspermia, by the way. The thought that maybe life from extraterrestrial origins is what sparked life here. Well, we know that the building blocks of life are created here, okay, as well as being delivered by comets and meteors and so forth. But could organic material have been delivered? Well, it's possible. The Murchison meteorite that fell some years ago, acids in it that look pretty interesting. So is it possible that happened before? You betcha. It probably is. So did an extraterrestrial bacterium alter the path of life on the Earth? Was the Permian extinction event, just one that occurred on our planet, or did it occur on a larger scale across the solar system through some type of event that was solar system wide and propelled debris to the Earth that may have had dormant bacteria in it that changed the course of life on our planet? You see the questions here? This gives rise to a whole bunch of questions within the panspermia thought process. And so, life having been seeded here in some way, I think is an interesting concept. So could any organic compounds that may have left Europa or Enceladus have made their way here? Maybe a large asteroid hitting Europa at one point or Enceladus could have blasted off chunks of material that came here eventually. Now, I say eventually, and what does that mean? It means it would probably take, millions of years for something that far away to make its way here. But then again, we got hit by an asteroid that was probably in our asteroid belt, then finally made its way here. You remember this talk, hopefully, at the leading edge of our asteroid belt, as soon as you get to it, there's a family of asteroids in one section called the Florians, Florians. The Florian asteroid is very likely the one that caused the Yucatan impact, which killed the dinosaurs. All right. Well, of course, it probably took millions of years for that to get perturbed out of the asteroid belt and make its way here. All right, into the inner solar system. But it did. It got here, and it did what it did. So maybe this could have happened. See, that's the thing about the universe. It has nothing but time on its hands. And I really think that's an important thing to make clear, So it's possible. Now,
and is that why we're making a defense to try to prevent this from happening again? The not near Earth objects, but
but the NEOs, the near Earth objects, are important. You're absolutely right, Amanda. And there is something we're going to talk about a little bit later called the Sentry table. It's a table we've talked about before, but I'm only going to briefly talk. And it's a table that actually gives us the risk for asteroid by asteroid, in our local space, the near Earth objects. Now, we don't have to worry about the asteroids out in the asteroid belt. We have to worry about the Earth-crossing asteroids. And we're going to talk about those, actually. And it's the later topic actually for tonight. I think that people will enjoy that, But
I mean, you don't really think about. I mean, I didn't anyway, about the defense kind of for preventing them, for destroying them, for rerouting them, all that kind of stuff. But one properly sized, properly placed asteroid can do a lot of damage, obviously.
Yeah.
It's kind of important, and it's kind of scary that we don't really have any defense for it.
Well, it's true. And our science there's all kinds of thought processes on the table. And NASA says they need about 5 years warning to come up with a mission to divert an asteroid. That's current.
Yeah, that's not
5 years. Yeah. Well, I mean, there is asteroids. I mean, and the asteroid we're going to talk about later that OSIRIS-REx is currently orbiting, perfectly, I might add, Bennu. Okay, that asteroid is in the Century risk table as well as a risk to the world, actually. But the potential risk is up around 2035 or beyond. So we would have the 5 years we need to mount a protective thing. But we have to find the asteroids first. You see, we have to find them to know if they're a risk. And we have to solve their orbits first. So there's a lot, that has to be done.
You know how you were saying earlier in the show, our calculations might be off, and we might be orbiting either more often or less often than we previously assumed.
What do you mean in the galaxy? Yeah.
What if that's the case? Could the predictions on that chart be wrong too?
And that's the predictions for the Century risk table are predictions for asteroids within our solar system. That wouldn't affect the positioning of the Earth around the galaxy, and the way that it rotates around the galaxy with the sun would not be affected. Would not affect, I should say, the predictions in the Century risk table. It's a wholly separate object. Luckily, they're not related to each other, so it shouldn't matter.
Okay. Well, no, I just thought if our orbit, hopefully that's the right term, if our orbit was altered by, several orbits.
Well, it's the orbit of the sun that's been altered, not the orbit of the Earth.
Oh.
It's the orbit of the sun going around the galaxy. See, we go around the sun, but then as a whole, all the planets keep going around the sun as the sun itself goes around the galaxy. See,
well, I'm just wondering if the sun going around the galaxy was sped up, would that speed up everything else? And would, if something's coming out in 2300, maybe it's actually 2100.
I understand what you're saying, but no, we would have found this before because, we actually put people on the moon. We successfully landed bodies on Mars, spacecraft. All of our calculations would have been wrong by the same amount based on the same type of problem had that been something that could have affected it. And there has never been any fudge factors required for doing these celestial mechanics studies. So it doesn't affect that at all. So, I guess, when we talk about, if we just go back for a second, if we go back and say, well, yeah, and we have a couple minutes left before our break here. And I just want to say, life on the Earth is something that was generated by the Earth itself. And if anyone wants to know about that, then they can look at something called the Miller-Urey experiment. That's Miller, spelled the way you think, and Urey, U-R-E-Y. And it's Harold Miller and Stanley Urey. They actually did a study to show that the Earth itself could create its own life building blocks, and it can, and that's a great experiment to show that, besides being delivered by comets and meteors and asteroids. Well, and that's also, we're talking panspermia, and now let's go back to the comets a little bit, and we're going to jump. We're going to do more on the comets shortly because we want to talk about the colors of the comets as well. Comets are only a few kilometers or a few miles across; they're not very big, Excuse me, and we know from having visited 67P, the Churyumov-Gerasimenko, that comets are really only just a few miles across, and they kind of look weird. They have this weird gooey look to them, it seems to me. But that's because of the nature of how they're made. They're icy bodies that have an accumulation of dust from their travel through the solar system for billions of years. And they are slowly evaporated every time they pass by the sun. And they were always considered these harbingers of doom, 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 doom. I like that. They were harbingers of doom in the past centuries. These periodic visitors to the inner solar system would light up the night skies with these long tails and bright heads, and people would be fearful. And there have been some correlations to historical events that you can go find and look up, which we're not going to discuss tonight. But it seems like people died when comets appeared and all that. And so it's kind of interesting, So then they're inert when they're far away from the sun, and they become active as they get closer to the sun. But we'll talk about more and talk about these greenish comets and what they have done to our history. Right back from this commercial break. This is Mark D'Antonio with Sky Tour Radio with Amanda Curran, and we will be right back. Hello and welcome back to Sky Tour Radio. This is Mark D'Antonio, your, crazy co-host. And I'm here with Amanda Curran, who's still here in the background, spinning around in her chair, whirling around. Here we go.
How'd you know?
Yeah, but she stopped so that she could look and talk into her mic. She's actually far away from me. I've never met her, actually. She's far, far away. Actually, I think that she's actually a real live human being and not like this artificially intelligent computer, which I've been accused of being. But I tell you, sometimes, before the break, we were talking about comets, and I really enjoy seeing them. I like photographing them and putting them out there in the observatory for folks to see. A lot of fun. And when Amanda and I do the Sky Tour live stream, we will often, if we image comets, we'll then go back and image them again and again and again in the same night. And you say, why? Well, it's so that we can then put those images all together and show you a progression from one to the other to show you can actually see the comet moving through space. They're very fast relative to the Earth because they're in an elliptical orbit. And as they get closer to the sun, they start to speed up. And they go whipping around the sun very fast and leave the inner solar system in a fairly quick manner, as quick as they arrived. So, but when we look at them and we observe them visually, what do we see? Well, we see they look like little fuzzy spots in the sky. And many times they're green. They have greenish heads to them. They look like a greenish head. Now, here's something interesting. That greenish head is not something that we see just because our eyes are sensitive to green light. They are most sensitive to green, okay? But it's part of it. It's really because that green is related to what's coming off of them. And we're going to explain that in a minute here. Now, the comets have a bluish tail that goes straight back in the opposite direction from the sun. And that means that no matter which way the comet's going, whether it's going toward the sun, spinning around the sun, and leaving the sun, that blue tail going out from the comet is always pointing away from the sun. So it actually is heading into its tail when it's leaving. Now, what is that? Well, we call that an ion tail. It's actually the result of a chemical reaction that's going on, and we'll talk about that shortly. And that's a bluish tail that goes straight back, okay? They also have these long gossamer dusty tails that hang back behind them. And that's the tail that you see most often reproduced in literature and taken in photographs. I remember seeing Comet West as a kid, and oh my gosh, you saw this beautiful head of a comet on the horizon and this beautiful dusty tail going up into the sky. It was all very clear. I was like, wow, it's massive. Look at it. had to be hundreds of thousands or more, millions of miles, actually, in length. And it was. And that was beautiful. And I didn't know what it was at the time, and I really wanted to learn what it was. And so what we have to ask ourselves, and what I asked myself, is what are comets made of that causes these tremendous colors, this green, this blue, and this yellow tail, that's this beautiful feathery tail behind it? What is all that? Well, we said before, when the comet's in deep space, it's just a dark, inert body with nothing going on. And it's an icy body, And, it's the same as any other inert object. It's out there, but it's different from an asteroid. I mean, an asteroid is rocky primarily. These are icy primarily. We'll talk about the ices shortly. Now, as they get closer to the sun, what happens is the sun begins to warm their surfaces and stuff begins to melt and float off the comet. All right. And that produces a sort of a fuzzy head that we see. All right. And then as they get near to the sun, we notice that they get these tails that develop, and they get bigger and more intense as the comet approaches the sun. And we've talked about it just briefly. There's two of these tails, in fact. One is called the ion tail and one is called the dust tail. So as the comet closes in on the sun, dust and gas move off the comet, all right, as this dust and gas is freed by the solar heating, and the material, the icy material on the surface of the comet begins to melt or sublimate, and this stuff moves off. Now, this becomes hundreds of thousands of miles in size around the head of the comet, okay? And the comets, remember, are only a few kilometers in size. And when they're millions of miles away, you can see them. So you can tell that we're looking at a lot of stuff that's floating off the comet head so you can see it. All right. So the surface of the comet and its interior is made of these ices with some rocky composition. But the thing we say ice, we think of water ice. Okay. Excuse me. But there's several types of ice. Not only water ice, which is H2O, hydrogen and two hydrogens and an oxygen, but different ices. You've heard of CO2 ice, carbon dioxide ice, or dry ice as it's called, and that's minus 109 degrees Fahrenheit and minus 78.5 centigrade or Celsius. But additionally, and especially after the Rosetta mission to 67P, we learned about this. The additional ices that were discovered include methane ice, CH4 ice, okay, ammonia ice, which is NH3 ice, carbon monoxide, CO. These five then, including the water and carbon dioxide mentioned above, these are the main ices on a comet. And as a comet approaches the sun, several things happen. The solar wind, okay, this stream of high-energy protons coming from the sun begins to increase in magnitude. And these ices begin to heat up, remember, from this previously inert nucleus. Now, the melting of the ice frees dust particles and molecules of this ice trapped in the deep freeze. Now, initially, when the comet warms up enough that the carbon monoxide, CO, carbon monoxide molecule can actually ionize, and it becomes this carbon monoxide ion, which has actually got a plus charge on the molecule. And what does that mean? It just means that there's a net positive charge because one electron was lost temporarily from the molecule. Okay, electrons are negative, protons are positive. Lose an electron, okay, you have too many positives, you have one too many positives, and it's a positive charge. Now, what does that mean for us? As the electron recombines, comes back, it loses energy by colliding with other things out there as it leaves the molecule momentarily. As it comes back to the carbon monoxide molecule, it drops to a lower energy level because it's lost enough of this energy. But as it does so, it gives off this blue light. And this is what we see in the comet's ion tail. And that's why the comet's ion tail is blue, because this carbon monoxide ion is created, and during this recombination, this electron that's lost temporarily comes back into the atom, or back into the molecule, into one of the atoms. It gives off this blue light. Okay, it's the same process with stars and nebulae. Why nebulae glow red? Okay, that's hydrogen atoms doing the same kind of thing where they ionize, and then an electron jumps back into the atom and gives off this red light. So the ion tail is something that always points away from the sun, as I said, as these gas molecules are pushed back by magnetic interactions with the solar wind, so that they always point away from the solar wind and thus, downrange basically from the solar wind. So that's why the comet's ion tail always points away from the comet. Okay. Now the dust tail, on the other hand, the dust tail is simply the material that floated off the comet, the dusty particles actually, and was left behind. Pushed along in part by the solar wind and then left in space. And these consist of small particles and dust. And these become the meteor showers that we will run through each year, right? The dust tail of a comet is what we're running through, actually. And so this, as the Earth flies through these every year from various comets that come through one time or another, we'll have these meteor showers. We just had the Geminids recently. We have the North and South Geminid shower going on, actually. So, we race through these different tails of old comets, and those become the meteor showers. The Leonids are typically spectacular because that was a particularly dense tail. Now, but what about that green glow we talked about earlier? Now, we see that green glow in the nucleus of a comet. What's that? Well, you see, here's something that is kind of interesting. Spectroscopy, the study of the spectrum of the white light we see coming from objects like the sun. Okay, it was invented around 1850 by a man named Joseph Fraunhofer. Now, he looked at the sun. He saw the sun had these dark, and based on these dark lines, he could tell what elements were, right? The same was done with comets. And as it turns out, a comet nucleus has two very important, components to it, okay? And these components consist of a carbon atom bonded with a nitrogen atom. We know that as cyanide, all right? And a carbon atom bonded to another carbon atom. So a carbon-carbon molecule. Now, for you chemists out there who want to know, these are covalent bonds holding the atoms to each other, okay? Now, when ultraviolet light hits these molecules, their electrons jump to a higher energy state and then drop down again to a lower energy state, releasing light. Every time an electron drops to a lower energy state in an atom, it gives off light. Every time it jumps to a higher state, it will absorb some. So we see that when these electrons drop to a lower energy state, after jumping high, then they jump low again, that jump down low gives off this particular green light. All right. And they saw that it was a cyanide molecule that was giving off this green light. Now, leave it to a good old astronomer, Camille Flammarion. And I want to thank Daryl for giving me an article on Camille Flammarion, which was really helpful in preparing this particular part of the segment. Okay. He was an astronomy popularizer and an astronomer from the 19th century and the early 20th century. And in 1910, he caused a mild panic when Halley's Comet was coming back. You see, because the spectra of Halley's Comet showed cyanide. And he basically spoke in such a way that people thought that as we passed through the comet, that, the tail of the comet, that the Earth was going to die and people were going to die from cyanide. Because it was known that cyanide, of course, is highly toxic to humans. And cyanide, as I said, shows a characteristic green color, like the other comets. And Flammarion is credited with suggesting that cyanide would hit the atmosphere and cause mass deaths. Now, he denied it, but look, once you're a Flammarion, you're going to always be Flammarion. I'm sorry. So the guy ended up being the guy who predicted cometary death. But the comets do have a green glow, and it is caused, by a certain atomic transition which emits the green light, and that's the cyanide molecule. So, comets are these interlopers, and sometimes they appear, one time, and sometimes they're periodic. We have, as humans, we've made amazing strides in our understanding of the comets. Okay, as we said a couple times already so far, the Rosetta mission to 67P. And again, the P means periodic. Churyumov-Gerasimenko. It was spellbinding. The comet appeared like it was two-lobed. Now, Rosetta was not the first comet mission. We said that before. There was Giotto, which went to Halley's Comet and did a flyby. And then there was a sample return mission, Project Stardust, with dust from a comet 81P Wild 2. And it returned it to the Earth. So we learned a lot about comets, from the previous information that we've discussed in the show. And we've actually learned a little bit about them by this discovery by New Horizons going to Ultima Thule, if you recall. So what do we mean by that? Well, Ultima Thule, if you notice, it looks sort of like a snowman, remember? Has that little circle, fat sphere at the bottom and a thinner sphere above. And was probably what's called a contact binary. And that means that these two objects were originally orbiting each other. And then finally, as their orbits decayed, they came into contact. Now, at the point of contact, wherever you have contact of something like that, there's rubbing, there's friction, however slight, and that will melt something. And so when you rub two ice balls together, okay, the chances will be that they will melt where they contacted each other and will refreeze almost immediately. So you can get a multi-lobed object this way. So that's what we think happened there. That's a contact binary, where they're actually in contact, two objects that glued themselves together, basically. So is that what we saw with Churyumov-Gerasimenko, 67P? It looked like it had two lobes as well, And the Philae lander from the Rosetta mission got stuck in a fissure, which is probably not there anymore. So the Philae lander has probably been freed, but who knows to what end? Because
I love Philae.
I know, wasn't it great? That little
land. Was so sweet. That was remarkable. That's quite the feat, and I don't think it got as much hype as it should have.
Well, do you remember when the Rosetta mission was occurring? I was most interested in Philae. Now, Philae is spelled Philae, okay? Go figure. But the Philae lander, not like fillet of fish, but Philae lander, was a lander that was supposed to get down to the surface and fire these explosive little bolts down to latch into the surface of the comet. And apparently, they didn't fire right. And so it hit and bounced off. Now, it bounced off, but see, it bounced several kilometers in the in the area around the comet, because the comet already had a very, very low gravity. So there wasn't, much force being, it's going to pull it back to the surface of the comet, but it did. And it bounced several more times before it came to rest in a fissure. And only by chance that when they went looking for it, they saw it as it was sitting in a fissure. Just incredible. So really neat stuff, and the thing that's interesting about all this is, we're seeing with the whole universe, the universe operates on a repeating schedule of stability for the most part. Other than the occasional supernova or asteroid strike, the universe has time aplenty. And that's something that I think is very important, because this gives us time to study it and time to actually figure out how to avoid dangerous issues that could come up, like an asteroid strike or a comet strike or something like that, or a large swarm of meteors coming in or whatever. If we can find them and we have time, we can fix it. We can figure out a way around it. Now, in an ongoing mission to asteroids, okay, we currently have the Hayabusa 2 mission, which is at Ryugu, which is a asteroid mission undertaken by the Japanese Space Exploration Program, JAXA. And that mission is going along swimmingly. They have rovers. They brought up, I think, 5 rovers to that asteroid that they're going to deploy over time. Just incredible. And because the gravity is so low on these small asteroids, to move around on the asteroid, they have this little lever that you're just going to flick. And the flicking action is going to cause this, again, for every action, there's an equal and opposite reaction. They're going to flick a lever. And this flicking of the lever is going to craft in the opposite direction. And so it's going to kind of pick itself up and then land somewhere else. They can't really steer it, of course. But that is how their little rovers are going to roll around and move around on the asteroid Ryugu. That's Ryugu. It's really cool. And now we have just pulled into orbit around another asteroid ourselves with, and it's called the OSIRIS-REx, mission. Now, OSIRIS-REx is cool, not because it's just another asteroid mission, but I like the name. I mean, Amanda, what you've heard of Osiris from history, haven't you?
I have.
Mm-hmm. Have you?
I have. I'm trying to think of the story right now.
Okay. I mean, well, I can. I'm not trying to embarrass you or put you on the spot here.
No.
Okay, but actually, Osiris in history, mythology, was Horus's
Was he fed
father.
his own kids?
Oh, I didn't hear that.
Okay, I might be confusing.
You could be right, but I don't know. Okay.
I remember names, but I have to hear the story a little bit to remember. So take it away.
That's okay, because I didn't know, and I thought if you knew, maybe you could answer it for me. But it turns out that Osiris was actually the ruler of the underworld and the father of Horus. Okay, and you might say, "Wow, well that's cool." So they named this asteroid mission, Osiris, after Osiris. No, it actually has nothing to do with Osiris, believe it or not. Now, that's what they say. But Osiris actually has an interesting name that I think is probably the most confusing name for a mission in history. So to me, it sounds like they started with Osiris, knowing who Osiris was, and then said, hey, can we figure out what this could mean? I think they went that way. But the name actually means origins, spectral interpretation, resource identification, security, regolith explorer. That's the Rex part. Capital R, little EX. Okay. So that's what Osiris Rex means. Origin, spectral interpretation, resource identification, security, regolith explorer. What's that security part? You have any idea? What's that mean?
Defense.
See, yeah, defense against possibly asteroids striking us. And actually, that makes sense because Osiris Rex was in a perfect position to explore a little-known region around the Earth for these near-Earth objects that we have yet to be able to see because they'd be 60 degrees away from the sun and very difficult for us to see because they would only be visible around sunset for a very short time here on the Earth. Now, from space, we could do it differently. And with Osiris, it was going to be perfectly placed to view this location. And it's a location where we've only found one asteroid so far. But it's a location that is known as the Earth Trojans. Okay? Not like Go Trojans, like the team, but more like it was named after the Jupiter Trojans, the satellites that were 60 degrees away from in Jupiter's orbit that are at a Lagrange point where the angular momentum of the asteroids in their orbit is exactly canceled, I should say, or equaled by the gravitational pull from Jupiter and other objects around there. Okay, so the forces sum to zero at the Lagrange points. They're like parking spots in space. So that said, Osiris Rex is gone to this little asteroid called Bennu, and it's Bennu, and we'll talk about that shortly. But the thing about the visit of Osiris Rex to Bennu is that this spacecraft, again, it's one of the cool things about it, is going to sample the asteroid and bring some of it back. It's going to bring back a piece of Bennu to the Earth, and that's the cool part about it. It's a sample return mission. It's like, yeah, that's so cool. Now, let's hope it doesn't end like the last sample return mission, which was the first one since the Apollo program, okay, the Apollo moon landing program, okay, and that mission was called Genesis, and it was supposed to sample the solar wind. And unfortunately, the landing didn't go as planned, and there's a video. You can watch this you can watch it all come down, literally. So what happened was the Genesis mission was supposed to sample and collect in a material called aerogel, a very lightweight but very efficient material. It was supposed to capture particles of the solar wind, okay? And it did. And then when it was going to land, what it was going to do was it was going to re-enter the Earth's atmosphere, deploy a drogue chute to slow it down, get it below supersonic speed, and then finally deploy a main chute and then land softly in the desert, and they would collect the aerogel out of this unit. What ended up happening was they saw this disc-shaped object tumbling out of the sky, never deployed a drogue chute, and it began to stabilize a little bit as it hit thicker and thicker air. And no parachutes were ever seen, and it impacted in the desert. Now, what's funny is, if you listen to the NASA dialogue, you would swear that NASA was saying, we've got a UFO entering the Earth's atmosphere, and it's crashing. It's a disc shape. It said it. It was a disc shape. It's disc shaped, and it's coming down at high speed. No parachutes are seen, and it impacted in the desert. People would think a UFO crashed. And you would think that it would destroy all the data that the thing collected. It almost did, but there was one section of the aerogel that was untouched and still safe and secure, and that yielded 0.4 micrograms of these particles. That's all they got back from this mission that probably cost them $800 million at least. So it doesn't always go right, you see, but sometimes, if it can go right, we can actually get something out of it. And the mission, OSIRIS-REx mission to Bennu, is going to Bennu is actually going to help us in our understanding of what are called the Apollo asteroids. These are other Earth-crossing asteroids that are out there, and I'll describe what that means in a minute. But that's a carbonaceous asteroid, and that means that its composition contains lots of carbon compounds plus other rocks and minerals. Okay, but it leans toward the side of carbon a bit. And Bennu is, of course, one of these Earth crossers that we talked about, and it's in the Apollo asteroids. So that means it's a near-Earth object. So what does Earth crosser, though, really mean? Well, Earth crossers are actually these are actually sorry, I was just looking at something. I apologize. An Earth crossing asteroid is one that is in an elliptical orbit. I shouldn't say highly elliptical. It's somewhat elliptical, so that at its farthest part of its orbit, it'll be in an orbit that's greater than the Earth's orbit. But at its nearest part of the orbit, it's at an orbital aphelion, it's called, that's closer to the sun than the Earth. So it means at some point, because they're relatively in the same plane as the Earth orbit, they're going to cross the Earth's orbit. Okay? So the far end of the ellipse is greater than the Earth orbit. The nearest end of the ellipse of their orbit is less than the Earth orbit. So technically, they cross the Earth's orbit. And Bennu is one of those Earth crossers. It has a diameter of 1,650 feet, okay, 492 meters. And it's about a third of a mile. Now, an interesting note. Bennu is designated, it actually began its life way in the beginning of the solar system, and it doesn't pose us a risk. All right, but we're going to learn more about Bennu in coming editions, and it looks like a diamond. It's a gorgeous asteroid with very low gravity. But you know what? We're going to talk about that on our next show. So until then, I want to make sure that you remember that next Sunday we're going to have a live show while the lunar eclipse is occurring. And then after the show, we're going to go right to the lunar eclipse live here at SkyTour live stream. But for now, and on Amanda's behalf, I say you guys have a good evening, and I hope you enjoyed SkyTour Radio for tonight. So remember, keep looking up, folks, and good night.